After understanding the importance of the setup hold time requirements and their root cause, we must design the mid-signal circuit in a good timing margin besides any timing variation. But it's difficult to guarantee good timing over PVT for high-speed SerDes. Could you please tell me why we cannot borrow the Digital Systems Static Timing Analysis STA for our high-speed timing analysis? In other words, why should we apply the dynamic timing analysis for setup and hold time? As you learn in the Digital 101, although the static timing analysis STA is a good tool for analyzing the timing behavior of digital circuits, it has limitations in capturing dynamic effects, clock skew, sequential and combinational interactions, power analysis, and process variations. Also, even though the STA is a fast and exhaustive analysis of timing requirements without a need for any stimulus, it may still have false errors and less accuracy. Therefore, we are seeking a precise timing analysis for high-speed digital blocks, which may not have a great timing margin, but are small enough to handle a more complicated verification flow. Hopefully, the dynamic timing analysis DTA complements the STA by considering these dynamic effects, providing a more accurate and comprehensive analysis of the circuit's timing behavior and enabling designers to achieve better performance, reliability, and power optimization. To be clear, the verification in the DTA must incorporate the SPICE simulation precisely to capture the dynamic effects, such as the high-to-low or low-to-high transition, clock data skew, and jitter accounting for the arrival time uncertainty, power consumption, or supply-induced noise jitter, and process variations over different process nodes. Finally, the goal of the DTA can also help evaluate different process nodes with VT condition, different digital blocks, like static flip-flops or high-speed customized flops. How do we perform the dynamic timing analysis systematically? Think about the setup time requirement images for 5 seconds. Right, the first thing you need to do is to understand your flip-flops well in the setup time requirements. Remember, at your clock rising edge, the data transition before the clock rising edge must be earlier than the setup time window. Otherwise, the metastability occurs. Now, we need to know what the setup time is here by assuming the flip-flop is a black box. What should you do? Correct. Just move the data transition edge high to low, low to high in your test bench. Then you should see the clock to Q delay of the flip-flops is constant if the arrival time of the data is greater than the setup time's requirement. But as the arrival time is close to the setup time, now the clock rising edge, the clock to Q delay increases dramatically to infinity, which means the output Q is resolved because of the metastable behavior. Again, from the arrival time versus the clock to Q delay, Can you identify what the setup time requirement is? Think about the constant clock to queue delay image for 5 seconds. Correct. The corner of the flag region is the setup time requirements, but you could relax the value to plus 5% corner of the flag value if your timing is tight in the design target. If the process yield or variability might not be a concern in your application. How about the test bench of the hold time requirement? Great. After the rising edge of the clock, you should move the data transition high to low, low to high on the same test bench. Then you should get the same behavior as the setup time. Clearly, you can define the hold time requirements at the corner of the flag region marked here. Usually, I prefer to make a strict constraint for the hold time, since any data rate will fail if there is a hold time variation. As you can see, the bigger bit period will lead to a longer arrival time than a setup time. Therefore, a setup time is easier to meet at a lower speed, but the arrival time after the clock edge is the same, no matter what the bit period is. Then, if the data transition after the clock edge violates the hold time, it doesn't matter if the bit period is greater or less. After getting the setup and hold time of the building blocks, such as the flip-flops, how do you make sure your whole high-speed digital meets the timing? Think about a stimulus image for 5 seconds. Bingo! We must add a stimulus for the data and clock in your verification or design target. Since both the data and clock are synchronous, the timing diagram shows you the phase delay between the data and clock transition is bounded. Then you should measure lots of arrival time difference of the clock lagging the data, TDS, then pick the minima TDS from every flop as your benchmark and see if it meets the setup time or not. Similarly, you should also measure lots of arrival time difference of the clock leading the data, TDH, from each flop. Then pick the minima TDH as your benchmark if it meets the hold time or not. Is this enough? Of course not. You should run the timing check over PVT. Okay, anything more? Think about the 30 speed image for 5 seconds. Correct. The data rate of any hard macro service is very wide. What I designed was 250 megabit per second to 13 gigabit per second, over 1 gigabit per second to 32 gigabit per second. If there's a timing variation in any data rate, that would be a shame. Therefore, we must also verify the DTA over data rate at least 1 gigabit per second step to exclude the possibility of timing hole, which we can not only avoid the timing hole by well-defined timing closure, but we can also catch it easy by the DTA over data rate. As you can see, the DTA of the data's early arrival time shows the raw data rate has lots of margin away from the setup time. But as the data approach to 13 gigabit per second, the timing margin is only 30 picosecond. Is that good enough? I don't know, since the delay or setup time may depends on different PVT conditions. How do we get more insight here? Think about a scaling image for 5 seconds. Perfect. The best scaling factor could be an inverter delay, but there are so many kinds of inverters of different sizes. If you remember the digital class 101, the fan-out of 4 inverter should provide efficient performance in the delay and power. Therefore, if we normalize the dynamic timing analysis in the fan-out of 4 delay, the timing margin should scale over PVT such that we may catch some mistake if there's a PVT case does not scale well. After normalizing the data's early arrival time, we know the 1.5 fan-out of 4 delay timing margin should be good enough for our 13 gigabit per second target. And even possibly, the 15 gigabit per second may meet the setup time right on the edge. For the late arrival time of the data, as you can see, the hold time margin is 2 fan-out of 4 delay over data rate, which is much more robust and safer. So far, we know the DTA is a powerful verification in SPICE, but sometimes we haven't started a design. As a project manager, how do you know if we can meet your timing by either choosing this process of this kind of flip-flops? Think about the timing requirements of a building block for 5 seconds. Bingo! You can create your own rule of thumb to judge if the process over the digital building block is good enough in your high-speed SerDes. For example, you may know the setup time and clock-to-queue delay of the flops and fan-out of 4 inverter delay respectively. Then you can add the total delay requirement to be the setup time plus clock-to-queue delay plus 2 fan-out of 4 inverter delay to be the clock period needs to be. Here are a summarized image showing why we should apply the dynamic timing analysis DTA for setup and hold time. Although the STA is a good tool for analyzing the complicated digital circuits, it cannot precisely capture dynamic effects, clock skew, sequential and combinational interactions, power analysis, and process variation of small but very critical and high-speed digital blocks. Therefore, we show how we precisely perform the DTA in SPICE model from block levels, setup and hold time of flops to a fan-out of 4 inverter delay, such that we can normalize the DTA over PVT and data rate for efficient benchmarking. We also show you a simple rule of thumb that is handy at the early stage of a project to help project managers choose the right process node and flip-flops or inverter topology to meet your needs. Hopefully, you will find the DTA is handy in your high-speed digital verification and design in the future. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.